Hi Akash, am I audible? Okay. Do you have any doubt in let's see, this week was particle kinetics. Today, actually, yes, yes, again, particle, what? I couldn't hear. You can message actually if you, have doubt in particle kinetics. So if you have any doubt, you can message. You can put message. I will check time to time. So let's start with our class. Let me check if. Okay, so recording is started. Now, first of all, regarding quiz, regarding the assignment 1 and assignment 2. So assignment 1 is primarily based on transport theorem. Assignment 2 is based on particle kinetics, and both last date it is by tomorrow. So I wanted to go slowly. So last class we had some example of 2D transport theorem. Today we will look at 3D transport theorem problems. So all formulas are same, just like how we can perceive thing, visualize thing. That is only the major part. Now this was done in previous class, and this we will do now. So before starting, if you have any problem, you can anytime write on the message. Moving forward, this is one of the issue. Okay, so right now what we are doing is we are majorly concentrating on this problem solving, so that all the questions are easily solved in a specific manner, so that you don't have any issue if a new kind of question arises. So, and first of all, we have to find these. So, kind of, this is step number 1. Find which frame are we talking about, which frame is fixed, and which frame is moving, and moving also with respect to what. Now next is, whatever quantities are given in the question, try to classify them into these three. Either angular velocities will be given, or angular acceleration will be given, or next position vector, velocity, acceleration between two frames, or position vector, velocity and acceleration between the moving frame, respect to moving frame. So it can be any of them. Okay, so this is step number 1. Step 2 is to find the position vector respect to fixed frame, and step 2 is nothing but just the application of the formula. So we will come to this formula later. First, let's have some basic knowledge about cross product. So if we have cross product of three independent mutually exclusive directions, let's say I, j and k, so we can have a formula such that in a cyclic rotation, in a clockwise rotation, I into j is equal to k, and j into k is equal to I. Similarly, k into I, k cross product I will be equal to j. So if we have this is the question, like there are different vectors given, b1 b2 b1 b2 b3, and also e1 e2 e3, and if someone asks what is e1 cross product e3, so first of all we have to check it out in this frame. This view, and when we look at this view, we have everything on a piece of paper, and whatever is not in piece of the paper is either coming out of the paper or going inside the paper. So if we look at E1 and E2 now, the first question is asked about E1 into E3. So when first of all, what E1 will be equal to is this one, and where is E3? Let us define E3 by some other color, blue or red. So it is going inside the, or it's coming outside the paper. So we know that whenever something is coming outside the paper, we denote it by cross, and whenever it's going inside the paper, it's by dot. So at this point it's coming outside the paper. So if it's outside the paper, we can denote it by cross, like it's coming outside. So these two vectors are defined, and if we have to find E1 into E3, it comes out to be minus E2. Why? You can roll up your thumb and try to find out which direction is this. So here we see it coming minus E2. Similarly, now if you wanted to find E2 and B3, now so the first question, now if you are looking at E2, which is given as this, and B3 is where this is B3. Now we wanted to find the cross product between this. So there is one way by which you can transform the vectors into different coordinates. So we can say if you wanted to find E2 in term of B1, B2 and B3, we can use that by using the cosine law. So this comes out to be like this, and now you can find the E2 cross B3 by using this expression here. And this will come out to be minus cos theta P2. So also we know that if there is some vector A, and if we are cross multiplying with same vector, it comes out to be 0. So here B3 cross product B3 came out to be 0, and B1 into B3, since it's anti-clockwise, so it came out to be minus B2. So here also it was anti-clockwise, like 1 2 3. So sorry, 1 2 1 2 3. So it came out like this, but in this question it was asked like this, so hence the minus sign was there. So this is all about sign convention. Also just revision of the formula. So here in the previous class we had this position vector, like if you want to find relative displacement between two vectors, so this relation is also there, like ARB is the relative, or we can say the displacement of B with respect to A. So let me just define what notations we were using. So if X is a quantity of interest, and anything which is superscript and right of it, let's say this, then it will be at what frame it asks, and if it's here, then it shows with respect to what. So this is with respect to what, and this is the new frame. And if some point is also mentioned, because that point will also remain in all those frames, so immaterial of which frame it is, the point is mentioned here. So it's like a point, just a point. It can be any point. So for example, this P is that point, and it is in both frame, in A also, in B also. So this is our notation. So this is displacement relationship. In relative, whenever we talk about relative vector, or we can also call it as finding of position vector. Similarly, there will be velocity vector and also acceleration vector. So if we check out the velocity vector, we see that there is also inclusion of this term omega. So omega is what? Omega is just a omega is angular velocity of B with respect to A. So here, if we assume A is fixed, let's say this is fixed, so B is yes. So this is omega of B with respect to A. So this is given by this relation, and the blue quantities are just the quantities mentioned in B but with respect to A. So it need not to be fixed, but if it's fixed, then this will be the relationship. Otherwise, these blue quantities will be there. Okay. Now, do you all watch movies? It is not in the course, but then also I am taking those examples. So this is from Harry Potter. If you are not willing to reply in like, okay, cool. Okay, so why this is relatable to why this question is relatable? So there are a lot of so in this there was one instrument by Hermione which was given by the Dumbledore regarding reversing of the time. So okay. So what happens that it is very strange looking thing in which she kind of give turns to this knobs and it changes the time. So there were three movements or three rotation in three directions. So that was the keen thing regarding the example. So you'd have seen the movie. There were a lot of things moving or evolving. Hello, is it working now? Okay. So the point is, like, there were a lot of movements, and we will talk about those movement in just after this, because whenever we talk about 3D, we have a lot of sense into visualization, because rotation can not only be done in one direction, it can be done in now three dimensions, or it can be done in lot of other directions also, if we take combination of all three directions. So that was first question. So it is called time turner. So why I am taking the example is not because of the physics. Actually, time has nothing to do with that, reversing of time. What I am more interested in its movement, how the movements are there. So next is this. So this is from uh, Inception. Any answers? So this is like spin top. We call it spin top. So it's just a spinning top, nothing else. Okay. So just giving a brief interview about the angles. So we have some angles called, like, it has lot of names, and here is the time turner. So here is the time turner, and it has lot of movements. So first is yaw. So if you take aeroplane in your mind, since I am an aerospace engineer, so I go by this example because lot of rotation can be understood by this. So if we are moving forward in an aircraft, you are sitting in a pilot seat. Now there will be something called in which way we are heading. Okay, so in which direction we are taking turn. So that is called yaw. Then the elevation or going up down. So that is called pitch. So it's like the aircraft is now pitched up. And then roll. Roll is bank. Also bank it also called also roll. So we can also define it in this sense. Here you are looking at the time turner, and it is having three concentric circle at an instant, and after that those circles are not concentric and they changes their rotation. Okay, so one configuration can be this, other can be this, third can be this. So actually it is a movement in three directions. So observe it. Now these are called ZYX Euler angle, or the nautical angle by which we move, like we take the direction sense using this. Also Cardan angle or Ted Bryan angle. Now there is one more expression of these angles, for it's called ZXZ Euler angle or proper Euler angle. So it is defined as spin, precision and nutation. So if we have spinning top, it can be understood using this spinning top. So that spinning top is, it is also so it has two, like rotation. One is rotation. Okay, so this blue one, this spin. So one motion is this spin, then there is something called precision. Now precision is at how much tilt it is, okay, and that too can also change. And the last is nutation. This nutation we also call wobbling. So if you can understood by this example, okay, otherwise take example of earth. Now earth is doing the rotation, it's spinning around the center of the earth, also it's tilted, so that is like precision, and also it is wobbling. Now what is that wobbling, I will tell you when this whole transport theorem is done. The wobbling is like due to others kind of movement, other movement. So the relative movement of the earth is little bit not exact as this two motion, there is some nutation there. So the rotation is there, nutation is there, and precision is there, okay. So this is called wobbling, that nutation. It is also periodic. Just to have clear idea of the 3D. Okay, so now we come to the first example of this 3D transport theorem. We have weather. Do you know how weather are formed, like on earth, why we are experiencing monsoon right now? Anyone, any idea? Sorry. Anyone having any idea? Yes. Yes. Okay. How it's changed? Like, can you be little detail? Little detail. Okay. But if it's perfectly be like this, like there is no precision or there is no, like it's not tilted, then also weather will happen. Okay, what causes this weather? Like, if we ask in a crude sense, what is the thing which causes this weather? Okay, Bimla replied, what by the movement? By the movement of what? By movement of the earth. Okay, yes, by the movement of the earth, weathers are formed. But what actually gives this force? So let's answer this. So there is a powerful force, by the way, and it affects the weather pattern. Okay, and it affects the ocean currents also, and it actually affects whatever is traveling on the earth, even the satellites or the planes in which we go. So everything is affected, and that effect is called Coriolis effect. Okay, today we will, first example we will just there is no numerical here, it's just understanding. Today I will show you how weathers are formed and at what part of the earth which weather patterns are there in a very crude sense. So in simple terms, the corrosive effect make things like plane or current of the air traveling along the distance around the earth appear to move at a curve as opposed to the straight line. If I say like I launched one missile from here, okay, and I directed it toward let's say Pakistan. Let's say some area here is Pakistan, and I directed this missile there. All right, like this, and I aimed at that Pakistan and I fired. Will that hit Pakistan or not? That is the question. It's the same question which was in last class we had discussed about the ant moving on the rotating frame. So it will actually miss. It will go like this. Okay, I should use some other color. So it will go like this. It won't be going to the same direction. Okay, let's discuss it more. So we know by the fact that different part of the earth move at the different speed. Like if you are at this point where the man is standing, the speed of the earth is, the rotation is 0 because he's just standing there. Okay, like so as earth rotates from west to east, which means counterclockwise as viewed from the above the north pole, we know that v is equal to omega r. Okay, so this r is 0, hence v will be 0 kilometer per hour. Now as you go, omega by the way here is 24 hours, so one rotation in 24 hours, right? So we can find out omega with this. Now r is the distance or the radius from where we are talking about. If we draw a central line passing through the north pole to south pole, we can say that at this point the north pole is there, so hence 0 distance, but at this circle the radius is, let's say, r1. At this circle, which is the largest circle, and it's called, at this point the circle is called equator, and again at this point this circle is called something else, so which is smaller than the equator. Right, we can observe that the speed kind of increases and it becomes maximum at equator, and then again it decreases and it becomes 0 at south pole. So it takes Earth 24 hours to rotate at one time. If you are standing like just a foot from the south pole or north pole, it means that 24 hours to move in a circle. And so if you are about 6 feet, so it will be 0.0005 miles per hour. So that much speed you will have, very slow. Now if you hop into equator like this person, so if you are here, okay, at this point, now omega will be same, but r is now very large, so hence v will be very large. Okay, and it will give about, the man is actually, it is not at rest, it is at 1670 kilometer per hour. Can you believe what is you have that much speed? It's like if you are going in a vehicle of 100 kilometer per hour, so this is 16 times that, nearly 16 times. So even though we are all on Earth, how far are we from equator? It determines our forward speed. Okay, the farther we are from the equator, the slower we are. So now also it doesn't answer the question that how variation of the speed it prevents thing from traveling in a straight line. Like I wanted to fire Pakistan, but it went to somewhere else. Okay, so let us understand that via simple animation. So let's say two trains are traveling. Is the animation visible? Like, okay, so let's say we have two trains, the red train and the blue train. So and you are traveling so you are traveling in this blue train which is very fast, okay, and there is a train red train which is slow. Now you are always prepared with a ball, football, and you wanted to just goal in that red train. There is a goal post in the red train. If they had been the same speed, and if you kick the ball and if you aim for this goal, you would reach it, okay. But what happens if that speeds are different, okay. So let's say you take an incredible shot, okay, just to the point, and the ball travels the side and misses the net. Now you wonder what happened. Like you started cool, like because you saw the goal post, you thought that it's just perpendicular to me, now I will just take a shot. But after some time, what happened that ball just misses the post. So now you are now only one thing you can do, you can just try to visualize that post somewhere else, okay, and hence it gives the curved path. Now let us see, this is the example. Have you understood up to this point the train example? Can you see that ball curving? Let me just try to draw that the ball started at this point, okay, and then it's going toward this. So like this it's going. Let's see. Okay, little bit at this direction. Like this is going. So like this it's going. What we expected was this direction, like a linear direction. We thought it will go in the pink direction, but actually it went to the red direction. It got curved because as you see, when the ball is passing at that point, the net is passing at this pink point. Let me make those points. This is our goal post, and at the same point here is the ball. Okay, just check here the shot is made, and yeah, okay. So it is the ball misses the post. Now let's pretend that these trains are on the earth at different latitudes, and add another red train in down also, okay. Now think of those red train as northern and southern tropics, and blue train as equator, okay. Like those lines we have drawn, these green lines are these trains. Now the red trains are going slower than the blue train, and remember that farther you go from the equator, the slower you move. Alright, now let's put our train in an actual earth shaped globe. the train still move at different speed, but now they would appear to travel parallel to each other. Even though the red line are going slower than the blue train, that red train is going slower than the blue train, since they are traveling a shorter distance, they would appear from a bird's eye view to be going at the same speed. Okay, this doesn't mean that your trick shot would behave any differently, but from bird's eye view it would look like this, that red line, right, which I drew, it will be something like this. So hence this curving is done, and the reason is solely because of Coriolis effect. So this is the deflection which I was talking about. So there will be a deflection, and anything traveling long distances such as air current, ocean currents which are pushed by the air, or the airplanes, okay, they all will be deflected because of Coriolis effect. It's like you are moving and the earth is also moving, and because of that variation in the earth movement you get this effect. Weird, right? This actually gives the phenomena of uh, cyclones and tropical monsoons and those things. Also, point to be noted that if you uh, look at the area above the equator, we get counterclockwise hurricanes or cyclones, and if you consider lower part of the area than the equator, then it's a clockwise rotation. We actually lie on the upper part, and hence we get this kind of behavior. So this is India. Okay, can you look at this giant cyclone? Last time also we also talked. So this is equator of the Jupiter, and again this is, can you tell which direction is it, clockwise or anti-clockwise? This is also clockwise. Also, if you go to the southern part, you will see that the sink the sinking is happening in the clockwise direction, as opposed to the counterclockwise direction which you right now see in your sink. What happens when we are at equator, like exactly in the equator? That means there is no spinning. Let's see, you have to go to equator. Anytime you visit equator, just check it. Okay, just go and fill the sink with water, and then try to see what happens. See, always there is, you will be either side of the line, you won't be exactly on that line, hence it will depend in which direction are you. If you're north side, then it will go counterclockwise. If you are southern side, then it's a anti-clockwise. Yes, it will spin. Okay, now coming to the another example. I think this is example 2, example 3. Example 1 was weather. Okay, example 2 is cyclones. Or hurricanes. Third example is focal pendulum. Now focal pendulum is just a pendulum, and it is just, I will highlight the focal pendulum in this. So this is that focal pendulum. This green part, just a string attached to a very large structure. So it is, uh, it actually demonstrates that Earth is rotating. Since we have little precision, or the Earth is tilted, hence this rotation, Earth, from the Earth rotation, we get this diagram. Let me just show you. If it had been a simple pendulum, it will take t is equal to 2 pi by omega, okay, and it will just go planar. But if you take account of the 3D, so it gives this arc kind of movement depending on at where it is located, okay. So it will make something like this kind of. After 24 hours it will be again like this. So when a focal pendulum is suspended at the equator, okay, the plane of oscillation remain fixed related to the Earth and at other latitude, and also you can find that omega. This omega will be 360 degree. This is the angle. So this angle is called latitude. So it's called sine of the latitude. So if you use enough wire length, okay, the described circle can be wide enough so that the tangential displacement along the measuring circle or between two oscillation can be visible by eye. So if it's very small pendulum, it will be doing something like this, but it's very large, hence we need a structure, a very big building. So it goes, this is enhanced. So there is also clocks made from this. How it's done that it is divided into 24 parts, and at every point a bead is kept, okay, and whenever they strike this bead, it actually gives it how much time has been passed in a day. So there are various focal pendulum. Even our new parliament will also have one, which is, I think it's being constructed or it already been constructed. But there are a lot of focal pendulum in the world in museums, so you can check it out as treasure hunt. So it also is affected by the Coriolis effect. Okay. Now I have a very interesting question for you. Now, Oh, okay. Let me just add one more point at an instant. So this is all happening at an instant. A jet plane is about to take off from the deck of a maneuvering aircraft carrier as clicked in a photograph. So let me show you. This is the photograph and this is that aircraft carrier. And this aircraft carrier is kind of turning around, okay, like it's now it's yawing. Now another thing is, so it's maneuvering. Now at the instance, I have already written at the instant shown, the ship is moving at omega 1 and omega 2 as indicated, where both angular velocities are defined with respect to the fixed space or ground. So omega 1 is this, like so there is one fixed point O1 and it is going round it, okay, that is first moment omega 1, and omega 2 is, it is also tilting. So omega 1 and omega 2 covered, where both these angular velocity are with respect to the fixed space. So there is one fixed space. So this is fixed frame. Then there is ship's frame or aircraft carrier frame. Then third is that there is aircraft on it. Now the airplane is moving with a velocity v0 and acceleration a0, both defined with respect to the aircraft carrier. The ship was defined with respect to the fixed frame, but the airplane is defined with respect to this aircraft carrier. Now airplane is also climbing with angular velocity omega 3 and angular acceleration alpha 3. Now both are defined with respect to the aircraft carrier. Now find the velocity. Now this we have to find out. Find the velocity and acceleration of the pilot P. Now obviously pilot P is sitting inside the aircraft. So pilot P is here. Also pilot P is here also. Pilot P is here also. But what we have to find is, we have to find velocity and acceleration of pilot P in this frame, okay, fixed frame. This is aircraft carrier and this is aircraft. This thing is turning like this. How can I, okay, this ship is kind of turning like this with respect to a fixed point. That fixed point is somewhere at here, okay, here, no? Yes, this is O1. Now it is also tilting like this. This is omega 3, omega 2. And this is omega 1. Omega 1, omega 2. And there is aircraft which is also doing a lot of things. first of all, let's define the coordinates. So green is the ship's coordinate, blue is the fixed coordinate, and orange is the aircraft coordinate. So let me go one by one. So this is the ship. So now everything came to the ship. Now everything came to this aircraft, and this aircraft is, the motion is defined with respect to the aircraft carrier. So that is the issue we are having. We have to find this P, the pilot's movement, with respect to the fixed point. Fixed point is where? It's out here. So that means the person is seeing from at this point what velocities and positions will he see. So only velocity and acceleration will he see. Okay, let's say a sniper is sitting at this point, okay, and he wanted to shoot that other person. So what kinematics he will take into account to do that? So first of all, the method is, first define everything. We have defined frames. So we have 3 frames. Then we have to define the quantities. So we are defining these quantities here, whatever is given. Also distance are also mentioned. This is B from the center of the aircraft to the pilot's place, and H is the distance from the surface of the aircraft to the top of the or the center of the aircraft to the center of the aircraft carrier. And also we are assuming that O2 and O3 in the single line. Okay, we'll go one by one. First, let's convert all the aircraft terminology into aircraft carrier. Okay. So here we had named the coordinate system. This one is called R3, this is R2, this is R1. Everything eventually we had to find it R1. So first we are transferring everything from R3 to R2, then from R2 to R1 we will go. So we are defining the displacement of R2 with respect to R1 with respect to R1 with respect to R2 R3 with respect to R2 we are finding, and with respect to R3 we have. So we are filling up the details. This is the position vector formula we are using. In this, what is known? This thing is known as distance from where R3 and R2 are. So this is B in one direction and H in another direction. Okay. So it comes out to be this thing. Now it gives us the position of the pilot from the aircraft carrier. Now another is velocity vector formula. In this, which we know that velocity of this point with respect to r3 is 0. Like that pilot is sitting inside the aircraft, it's not moving outside the aircraft, and it's not moving with respect to the aircraft, it is stationary with respect to the aircraft because seat belt is on. Now the omega we are also defining here because omega of the aircraft is given with respect to the aircraft carrier, and we can define it in form of vectors. Now this come out to be this thing. You can look at the figure also. Right now what we are doing, we are converting the frame from R3 to R2. Everything we are putting on R2. We just found out the position vector. Now we are finding out the velocity vector, and once that is also found out, now we can move on to the acceleration vector. This is a huge expression. So first we will look at the acceleration of frames. So acceleration of frame from R3 respect to R2 is A naught. I think this will be A naught. And the velocity from respect to R2 of R3 is V naught. Now acceleration of R3 respect to this point is 0 because that person which is sitting in the aircraft is bounded by the seat belt, so hence the acceleration of the aircraft and the pilot are the same. Now the alpha is the angular acceleration, that is also given alpha 3, and other quantities are known from the previous quantities. Now it gives the acceleration vector of R2 of the pilot with respect to R2. Now once we did that, now we can find motion of O2 with respect to O1. So R2, now we can come to R1. So these are the formulae. These are the known quantities. Now these are the formulas which are used. So this is acceleration form, also velocity formulas used again. And this is the acceleration formula, the huge formula. And these are the answers. You have doubt any in any part up till now? It is all happening in at an instant. Any doubt, Akash? Okay, so how this velocity vector is defined is this formula. This, okay. So this formula, if we just talk about velocity, so velocity of any point with respect to the frame which we are asking will be the velocity of the frame with respect to the moving frame, and also this term, additional term. So this omega r will actually add upon that. Okay, so it is combination of three terms. One is the velocity of that point with respect to that frame, plus velocity of the point with respect to whatever frame it is asked, and plus omega into r. Similarly, when we come to acceleration, we actually are using transport theorem. So let me show that. If you have missed last lecture, so all those are defined in form of transport theorem. So this is the transport theorem, relationship between the inertial and non-inertial frame. Inertial frame are frame having where everything is fixed, and non-inertial frame in which it is moving with respect to the inertial frame. Now coming to next example is missile trajectory. I told you that if we fire a missile, then what will happen? So Earth is a rotating frame, we know, and the angular acceleration, angular frequency of this rotation of the earth is, we can find out, because we know it rotates in 24 hours, right? So we can find the whole rotation speed, and it comes out to be 7.3 into 10 to the power minus 5 radian per second. Very small, but the point is, like, so we have some question. So do earth rotation momentum get transferred to any object when it is getting launched? Okay, and if so, why do we have considered earth rotation while launching the missiles or rockets? So if you build a rocket and you launch it close to the equator, okay, so you can use that to reach the orbital velocity if you're just pointing outwards. But what happens if it's not in the equator, it's some place else? So like this. Okay. Let's say North Pole, you have launched a rocket to the South Pole, but that thing is not actually going to the South Pole. How? You can see like here. So it is curving. So for an object in motion with respect to the earth, the largest non-inertial force is Coriolis force. Okay, the 2 mv omega, and this omega is the angular velocity of this earth around its north pole or south pole axis. And if we neglect the other three smaller non-inertial forces, the equation of motion of projectile will just be A equal to G plus 2v into omega. So that Coriolis acceleration. So as it travel long distance on the earth, the Coriolis effect is responsible for many large scale phenomena, and so fast moving objects also get impacted by the weather. And now let's say aeroplanes and rockets are there, they also get influenced by this, and this effect largely determines the direction of the prevailing winds. So whenever the pilot is flying a plane, he takes account of those patterns. And even the next question is about sniper. If we look at the snipers, and if they are taking very long shot, first of all, do you know that this is the record, like the Craig Harrison, who recorded at 2.4 kilometers nearly. So bullet traveled for 3 seconds before it hit the target. And military snipers consider this Coriolis effect. It could be some or centimeter, but it is counted, because if you will see at this point, having about 2.5 kilometer, and with this speed, and for 3 seconds, it comes out to be 0.5 meter. It's like 50 centimeter. 50 centimeter is this much, right? So the target misses by this much if it's traveling 3 kilometers. So although bullet's trajectory is minimal to the significant affected by the Earth's rotation, sniper targeting is so precise that a deflection of several centimeters could injure innocent people or damage civilian infrastructure. So hence sniper take account of this correlative acceleration. Okay, this is the homework if you wanted to solve. Like the attempted path, it is just like Pakistan one problem. Like if we fire missile here, assuming this is Pakistan, it will actually hit at some other point. We will have some sideways slip. So this is a question where we are finding correlative acceleration as well as what the resultant velocity at this co-latitude 43 degrees will be. Okay, if you have written this formula right, but otherwise we will be needing it more. So in next example we have an airplane moving with velocity v1 and acceleration a1 both respect to the ground. Okay, now ground is fixed here. It is banking at omega 1, climbing at omega 2, both respect to the ground. Again, these omegas are defined respect to the ground. Now an antenna whose mass is m is being deployed from the airplane. That airplane is in a horizontal orientation respect to gravity, and antenna P is at vertical distance of d from the center line of the airplane, moving with velocity v2 and acceleration a2, both defined respect to the airplane. So now there is one frame at airplane, another frame is at rest or at fixed, it is fixed somewhere in the space, and third is the antenna. So again the question comes out to be for at an instant what is happening. So we have reference frame A which is fixed, B which is the aircraft frame. So first we will define all the quantities. So omega with respect to A, omega of B with respect to A is given as omega 1 I cap plus omega 2 k cap. So fixed frame is defined by the capital I, J and K, and moving frame is defined by the smaller I, J and K. So we are applying these formulas. So let's see this position. Now we have to find the antenna's displacement with respect to fixed frame. So it comes out to be antenna's displacement in the moving frame plus how those frames are moving with respect to each other. So at this point it is d, because how much distance it is there, that is only. Now coming to the velocity. This velocity is defined by what is the relative velocity between them and also velocity of that point with respect to the moving frame plus the omega between these frames as well as how much distance in between. So how much distance it is at, so it comes out to be this expression. And finally we are finding acceleration. So acceleration of point P with respect to the fixed frame, and it comes out to be this huge expression. So everything is at an instant. This is very important because we are not defining whole kinematic, but we are saying what if we change the coordinates, then what will happen. Okay, before going to the problem, so I think this is the last problem. This is the last problem, and it has huge lot of things. Okay, so I want that you should try this. So there are a lot of frames, references. So I think there should be some written thing about what is happening. Okay, in this question, so there are a lot of frame. First is fixed frame at this point. So n1, n2 and n3. So it is defined by r1, n1, n2, n3. Next frame to be defined is this point. Let's use some other color. Let's say green. Now n3 is same. N3 is same. Let us make this R2. Now instead of N2, this will be minus N2. And there is one more, D1. So R2 is defined as, instead of N1 we have D1, then minus N2 and N3, 3 vectors. So white frame of reference, then green frame of reference. Now coming to this point. This can be R3 and or better if we choose this point. So this R3 is there, having D1, then ER and E theta. So 3 frame of reference with all the quantities known. So we start with this point. This point is actually spinning around the point O here, and it's spinning by this thing. It is at distance h from this plate. Let's have some other color for this plate. Some problem is happening. Okay, this pink plate and that green plate again the same. It's actually not a plate, it's a same color will be there. So it's a ring, green ring. Now this green ring is at distance from this pink plate h, and this pink plate has radius r, and it is from distance lt and ht from this reference frame. Now we have to find we have already named them. This is n1 n, and this is d, and the last one is e. And angular velocities are defined as theta dot and psi dot. So just observe the thing. first here in this question only velocity is asked. It's very complex for the acceleration to fit into one picture, so hence we are finding the velocity, and that is this is the final answer. But there is an intermediate step in between where we have to find er theta and e psi, er and e psi. So this expression, okay, the cross product, which is little tough because n3 is here, like going upward, or it can also be said it is here, or it can also be said it here, and there is er and e theta. So n3 into er, we have to find that, which comes out to be this, by using the same principle we have discussed in the starting. So actually this example I put because of this question only. So if we have this kind of behavior, now how to find E2 in term of B1, B2, B3. So it's a similar question as that. So we have to take account of all the sign conventions. So let's look at the position vector. Position vector is pretty simple because this thing is at rest and this point P is moving. So it will have this expression which is having all those terms like n1, n3, d1, then again n3, and then er. The problem is with er because as we can see that n1, n3, d1, they are all d1 is not but n1, n3 and n2 are common everywhere. Okay, what is not common is d1, which is in n and e both, frame n and e. So next we apply the formula, and in which we get a cross product for which we don't have expression, hence we will use the cross product and find out this expression. So actually ER we are providing as cosine terms, sine and cosine term, and we are putting in term of n3 and d2. And if we put the expression of ER, we get this is the answer. So just to give a brief introduction to things, the angles. I will attach this also there. So how that cos theta and sin theta came out to be in the picture. So if we have 2D rotational matrix and we have OP with all the angles mentioned, how can we convert that x and b coordinate to some other coordinate? Okay, so it's like if frame is rotating, just rotating, then how to calculate that? So we can use geometry here to prove that theta, like if it's rotated by the theta, so you can try this as an example. I will attach this with the main report. So now from next class we have to start particle kinetics. So I will give you a brief overview of things. So if we start with the kinetic and dynamics of the particle, we can go into lot of direction. So one major is planar curvilinear motion, in which we can go to Cartesian. So where x and y component or acceleration are independent generally and determined. Or we can go to intrinsic, whose example is also circular motion. Or we can go to polar. So this is all kinematics which we had covered. So the general of this is transport theorem. Then there is relative motion. So area which we are covering, I will just defined by the gray. Looking good. So they are advanced topic. Once your foundation is made, so this is like foundation of things. This is how we are taught in our primary studies, secondary studies. For example, acceleration is constant, then we can find it using these formulas. Vt is equal to u plus at, v square is equal to u square plus 2as, and if it's not constant then it's a function of time, then using the integrals, those things. And if it's a function of displacement, then what happens? So all these cases we have already studied. Now next we will understand all these things also in from the next class. Like if we have a rigid body, then what happens? And what happens when it's a continuous bodies or flexible body? Okay, for example, we have just taken bars and beam, but can be modified to many things. So everything is connected, math, physics. It just depends what perspective we are talking about. Okay, this completes our class. If you have any doubt, you can ask. Meanwhile, I will just edit this document and upload it on YouTube. There was some written question. I will just find it and upload. Rishikesh, it's over. You can check out the YouTube video I will be uploading by tonight. So we'll be attaching the Corliss's effect like this whole lecture, but tonight you all can check out. So I'm ending the class.